Thank you all for coming today. You must be very dedicated to lock-free queues to want to sit through 2 sessions like this. Like I mentioned earlier, I'm going to build on Timur's presentation, and in about 3 or 4 areas. First of all, Timur had the concept of a T type, and for this presentation, we're going to assume that T is a plain old data or pod, which means integer, float, or conglomerations thereof. We're also going to look at security and multi-processes. We're going to look at the concept of multiple readers or multiple consumers, but from a different angle than the way Timur looked at it. And we're going to look at a couple other areas too. But let's get started. So I'm going to skip a lot of my intro material because of everybody having seen Timur's, and also so that we can fit more stuff in here. I will just mention that I absolutely love circles of all kinds, especially donuts, and especially circular buffers. This is my dog, Bella, here. Not the same Bella as yesterday, but it's what a great coincidence. So I'm going to skip through a lot of this early material, but I just want to build on one thing that Timur said, which is lock-free queues and FIFOs, circular buffers, whatever you want to call them, are incredibly useful. They're immensely useful, more than you can possibly ever imagine. And I have some great quotes from Timur from a video that he gave a year ago. So I'm now going to skip through all the definitions of queues and things like that and jump right into the material that continues right off after Timur. So I had a problem, and my problem was forks. Too many forks, basically. We had about 10, when I started, about 10 different copies of this lock-free queue code. And when I finished, we had about 15 different copies. Because while I was working on this, people kept copying the code and forking it. And so what my problem was is that I wanted to merge all these different copies together. And yet they all had different APIs, different requirements, and things like that. So it clearly wasn't possible to actually merge them. So instead, what I tried to do was merge the implementation, and then we're going to preserve the API that's on top of them so that all the old code will continue to exist. So it's a work in progress. I'd say I'm about halfway done. I think the implementation part is almost done. I haven't begun actually layering the APIs on top of this. Hopefully you won't have this problem, but if you saw Timur's talk, you're going to be all enthusiastic now and want to write your own lock-free queue code. So maybe instead of 15, we'll have 115 of these. Okay, so let me zoom through real quick and get straight to the circular buffer. Okay. So the motivation for the circular buffer is that if we just treat it as a simple linear array, then what can happen is eventually we can move off the end. So Timur explained that instead of sliding elements down, we'll just have these front and rear pointers that allow us to circulate. Okay. And you can call them circular arrays, you can call them circular buffers, same concept. There's a problem, though, that can arise when you use a circular array, which is, here we have one that has 3 elements in it, and we're going to start removing them. We're going to start popping them, okay? And then we add one more at the end. And now we have, we add 2 more at the end. And now we have a queue with 3 elements in it, but they're not contiguous. You can see that they go index 2, 3, and 0. And this is what I call the fragmentation problem, which is you have half of your elements on one side, half are on the other side. And there are a lot of different solutions to that problem. If you're only looking at the elements one at a time, it's not a problem. But if you want to look at multiple elements at a time, you have to solve the fragmentation problem. So this is what it looks like as a circular buffer. We have one piece of data, but in 2 sections. So I'm going to go through 4 different solutions to that. First of all, you can simply copy the data so that instead of being discontiguous, it's now contiguous. The second thing you can do is something called double mapping. This is a great trick. You can find more about it in the Wikipedia article. But basically, you map your page of memory that contains the circular buffer twice so that they're next to each other. Okay, this works fine for certain table sizes and things like that. It's not as portable. Next thing you can do is simply avoid the fragmentation problem by making an agreement that you will never, ever fragment your data. And the way you do that is, let's suppose we have a circular buffer with the size for 16 elements. You just agree ahead of, okay, I'm always going to put in groups of 4. I'll never have a group of 5. Right? And so at the fragmentation point, it simply never happens. Or there's another solution, which I call the embrace the problem solution, which is just say, I love fragmentation, it's great, I'll just deal with it. And what you do is you just keep 2 pointers to the 2 sections. And this comes from those of you who know Linux or Unix. It's called readv and writv is the API, and basically allows you to deal with fragmented buffers. You have a base and a link that point to the 2 different sections. This is my personal favorite approach. So next I want to talk about the indices, the front and rear pointers or indices. As Timur mentioned them, they're integers or pointers, and in the case of integers, they're in the range of 0 to the array size -1. I want to now talk about another way of looking at those offsets into the array. Instead of just thinking of them as raw numbers, think of them as a higher level abstract concept, which we'll call an index. So the offset is the raw number that selects the element of the array, and then the index is going to be the higher level concept that eventually gets mapped down to an offset. I'm going to have to skip ahead to get to this. There's direct mapping, where the offset is simply equal to the index. And you can see from this table, there's a one-to-one mapping here, and they're exactly the same. Or what we can do, actually, let me motivate why we want to go to the other one, though, is let's suppose we have front and rear both equal to 2, so the number of elements in the queue is none, is 0. And then we start adding. What happens when we wrap around, we have 3 elements in the queue. When we try to add one more, we have an ambiguity, because if we actually tried to put the 4th one in there, of course, you can't tell the difference between full and empty. And Timur said, oh, let's just not do that. And that is a perfectly valid solution. There is another approach, though. This is my graphic for the full versus empty problem. So instead of avoiding that last element, what we can do is we can create a new representation for our front and rear indexes. And what we're going to do is we're going to introduce something called modulo mapping, where the array offset is equal to the index modulo the array size, but we'll continue to preserve the full index in its original form. And now what we can do in the same case, I'm sorry, let me zoom ahead one more. Okay, in the same case, when we get to this case where we have 3 elements in the queue and we're about to what seems like an overflow, we can actually not overflow, because we can distinguish now the case of rear minus front is equal to 4 versus rear minus front is equal to 0. And so that allows us to use the full queue. And the reason this matters is typically when you have a queue which is a power of 2 in size, and you're using, like, let's say, a full page of memory. And if with the other approach, you would have to allocate 2 pages of memory, whereas with this approach, you can allocate a single page, so there's no loss of memory. So let's continue, though, past the full point. What happens if the rear advances beyond 5? Timur mentioned one thing you can do is overwrite the least recently enqueued element. That's certainly perfectly valid. But there's other things you can do, and we're going to get to that case. But just for now, just assume that it's okay to have an overflow. It's not a bad thing. Try to keep that in your mind. Okay. Let's look at the index in more detail, specifically for modulo mapping. Okay, so we remember that the offset into the array is equal to the index mod the capacity. I'm going to make an assumption. If the capacity is a power of 2, then we can look at these as bits. So for example, if index is 6 and the array size is 4, which is a power of 2, then we can find the offset. Rather than dividing 6 by 4 and taking the modulo, we can just AND it with 4 minus 1, which is 3. This is another way of looking at it as bits. So we take that 6, get the offset of 2, and we now have another field, which we'll call the generation, which tells us how many times it's overflowed. Timur alluded to this during his talk. We're going to go into more detail here about generations and how they're useful. This brings us to our first circular argument. We'll have a few today. Some people love division, say, oh, just use division everywhere, you don't have to think. Other people are more traditionalist, embedded programmers, and they prefer masking. I'm not going to take sides here, but accept that masking is the right one. Let me skip this. Okay, so I'm going to talk about security, which is something that wasn't mentioned earlier. So security is when you have to worry about part of the system being correct and part of the system is incorrect, and you don't want the incorrect part to take down the other part. There's lots of ways that these indices can cause security problems. They can have invalid values, somebody can be overriding them, they can overrun all these kind of different things. There's solutions to each problem. For example, we can put the index into a separate page from the data and give it a different protection. And we can make it read-only to one process, read-write by the other process. And for invalid values, we can look at the value, and before we use it, examine it to make sure that it's reasonable, and if not, we can just say, hey, we're not going to deal with this queue anymore, we're going to reset it or something like that. Another kind of security thing that we have to worry about is that in traditional compiler implementations, it was perfectly reasonable to overflow your integers, both signed and unsigned. However, more recently, the standards are saying that it's explicitly undefined to overflow signed integer arithmetic, and it can optionally be undefined for unsigned integer arithmetic. The reason you would want to make it undefined is it allows the compiler to generate code that will do extra security checks, which is really useful for buffer overflows and hiding certain or preventing certain vulnerabilities. So we, in our team, normally compile with all these overflow checks turned on, but when you're doing the kind of bit twiddling that you do here with ring buffers, you really want to explicitly turn those off. So what I recommend is compile all your code with the safe options, but then explicitly mention only for the methods that matter to you to have them not have the integer overflow protection. That's a lot better than compiling the whole code with security checks turned off. Okay, this brings us to our next circular argument, which is how big should the indices be? Phil's eyes are lighting up. We have this argument all the time. Again, you could make it 32 bits, you can make it 64. There's good arguments either way about which size they should be. And again, I know the right answer. Phil knows the other right answer. But we won't get into it. On most architectures now, they're equivalent. You can use either one, whatever you prefer. How are we doing on time? Oh, we only have 10 minutes left. Okay, so we're gonna zip a little bit through this. Okay, capacity versus size. So here's a ring buffer with capacity of size 8, meaning we could put up to 8 elements in there. But there may be reasons why you want to temporarily not use all 8 of them. For example, you want to adjust your latency, and if you use all of it all the time, you're going to get a fixed size latency, whereas if you want a variable latency, you can temporarily limit it. The analogy that Phil uses, and I love it, is of a railroad train. Rather than having the caboose right next to the engine all the time, you can say that 2 spots on the railroad track are unusable, and so we'll limit our train to a size 6. And the way you would do this is simply at the in-queue step, rather than checking for queue full, you redefine what it means for the queue to be full and have a slightly lower threshold. Let's see. Next we'll get into blocking. Okay. So there's different kinds of blocking and non-blocking, and I'm going to try to go through several of the major types here. First of all, there's what I would call good blocking. And this is blocking where you want your thread to wait or pause because it doesn't make sense for it to proceed. An example would be if you want to dequeue an element from the queue is empty, there's no work you can do, so rather than spinning on it, you just want to block until the queue has something on it. That's good, that's safe. I love that kind of blocking. Then there's another kind of, then the converse of blocking, of course, is non-blocking, but there's two different kinds of it, and I want to go through, one of them is good, the other one is evil. Right? The evil kind is where you think that your code is going to continue, and if the condition is not satisfied, but actually internally there's some hidden mutex or hidden spin lock or something like that that may cause it to either block at the mutex or run for unbounded time. In one of Timur's code examples, he showed a while loop around a checking a condition. If we can know and be confident that that while loop will run for a maximum number of times, then it's fine. But if it could run for an unbounded number of times, then we have what I would call weak non-blocking, because there can be conditions under which it actually does block, but not in the kind of a way that you would want it to be. So be really, really careful of this. This kind of non-blocking is dangerous. Then there's then the other kind of non-blocking, which is also called lock-free or wait-free, is the good kind of non-blocking. And in this case, if you can't proceed, it will return to you immediately. It'll return false or something like that, and then you can do something else. But you can be confident that you will always proceed in some way. You will be able to go either take one fork or another, but you'll always be able to proceed. And this is the kind of non-blocking that you want to have. If you remember nothing else from this talk, I want you to walk away with one thing, which is when somebody says that their code is non-blocking, ask them what kind it is. Is it the kind that's safe or the kind that's unsafe? This is a really, really critical point. Then you can combine the two together. You can have blocking combined with strong non-blocking. And what that means is that it will either block in the way that you want it to block, or it will not block in the way that you want it to not block. All right. So, for example, the dequeue from an empty queue, it'll either say, sorry, the queue is is empty, I can't do anything, or sorry, the queue is empty, and I'll wait for up to 3 seconds to have an element. But it will never go into a state where it's spinning on the queue or something like that. This is also safe and perfectly fine. So next I'm going to go into some of the implementation. In Timur's talk, he talked about the compare and swap or compare exchange, and there was one other primitive used, but I can't remember. Yeah, exchange. Okay. Those are great primitives. I'm going to talk about a different kind of primitive, which also works well, but it only works well for plain old data or pod data, and I don't recommend using it if your data is an object or an arbitrary T or a reference or something like that. So atomics answer the question: when I'm reading an index or when I'm writing it, how do I read it? How do I read it? Or how do I write to it? And the way you do it is different depending on whether you're the reader or a writer, and also whether you're reading from the index or writing to the index. It's called load acquire and store release, and there's a sequence that you have to do in exactly the right order or it doesn't work. What you do is you load acquire from one of the indices. Based on the load acquire results, you can determine whether it's safe to proceed or not. If it's not safe to proceed, just get out of there. There's nothing you can do. But if it indicates that there's, for example, data there that you can read from, then what you can do is you can process the data in the buffer and then advance the corresponding index using a store release. And then your partner does the exact same thing, but in the other direction. The reason why it's so critical is because the load acquire guarantees that any memory reads in the blue section here on the reader side, any memory reads that are done here will be observed, that is actually executed after the read from the index. If you don't use this special kind of memory load, then they might be executed out of order, and terrible things can happen. And the same kind of thing on the writer side. There's some great articles on the web. I encourage you to read them. But in the meantime, just try to memorize that sequence, and it'll work for you. There's another name for this, which I call obtain release. And basically, it's the concept of splitting your queue operation into 3 stages. The obtain stage, where you get a reference to the data in the buffer that you're about to work with. On the consumer side, it's data that's been filled. On the producer side, it's memory that's empty that you're about to write to. Then the computation stage, where you actually do your thinking and reading or writing into the buffer. And then finally the release, where you update all your indices. And if you take this strategy, you can separate the different parts so that rather than becoming a single API, so rather than a single push API or a single pop API, it becomes a 2-part API, where you say, for example, for push, prepare to push, which returns a pointer to where you put the data. Then you can do your computation in place directly in the buffer. And then finally, you can actually commit the transaction with a release. This is useful when your data is very, very large, or you need to, and you want to compute it, let's see, in stages over time or something like that, and you don't want to copy it in extra time. So the acquire, the load, acquire, and store release basically answer the question, how do you read and write the indices? The Futex, this is a Linux-specific system call, answers the question, how do I notify the other side that I have updated the index? In the case of the obtain phase, it's how do I block? This is the good kind of blocking. And in the release stage is, how do I tell the other person to unblock? So I won't go into Futexes a lot. Again, there's a lot of material on the web about it. But it stands for Fast User Mode Mutex. But it's a great API, and I highly recommend using it whenever you can. How are we doing on time? 7 minutes, okay. So earlier I talked about the difference between your maximum size for your buffer, which is the configured size, the array size, and then the current maximum size, which is how much you actually want to use. I now want to introduce a third size, which is what size do you actually want it to be all the time? Using our glass of water analogy, so the capacity is the most that your glass could ever hold. But you'd be pretty annoyed if your waiter filled this up to that level. Okay, so you don't want to actually use your capacity. Then the size is the maximum that you would want to ever reasonably fill it up to. So you'd be happy. You're okay if your waiter fills it to that level. But it would be annoying if your waiter always filled it to that level, because it's just a little too much water. Right? So we'll now introduce something called the set point, which is sort of the goal. This is where you want to keep it all the time. And this is a term that comes from control engineering. So let's go back to that water. Here we are at 1 level, okay? Then you drank a little tiny bit of it, okay, so it goes down. So your waiter comes back and fills it up again to the desired goal. You drink a little bit, and the waiter is just hovering there. It just keeps filling, unfilling. I don't know about you, but I'm getting really dizzy watching this. Okay. So I think you can see the problem here, which is we're having too much context switching. Here I am trying to work on my tablet and on my laptop and on my notebook all at the same time, and I keep swapping back and forth. This is really inefficient, trying to maintain the set point at exactly the right level. So again, we'll adopt another concept from control engineering, which is hysteresis. We'll have 2 more levels, so we're up to 5 levels now so far, which is the set point, which is the goal, and then we'll have the high water mark, which means we'll wake up the reader if it gets to that level so that the reader can start draining. And then the low water mark, this is the waiter's trigger, which is the waiter will come by and fill up the water or if it gets below that mark. So now what happens is instead of hovering right around the middle, we go back and forth, and we can reduce the number of context switches between the reader and writer, which can be much more efficient. Earlier I mentioned that it was going to be safe to have overflow, so let's talk about that, okay? Not this kind of overflow, but this is the kind of overflow where rear minus front is greater than the capacity. Okay, and when would this make sense? And again, Timur actually talked about this, so I'm violating my promise not to repeat anything here. One good use for it is logging, where it's okay to lose a little bit of your log. He mentioned also the example of the audio waveform display. Another use for it is broadcast. Timur described the multiple consumer use case. This is a different kind of multiple consumer use case where all of your consumers are going to receive the exact same data. An example might be, let's suppose you're taking your audio data, you're playing some of it out to the speakers, some of it's going to the waveform display, some of it's going to a debug log. So we have so far 3 different readers for the same data. What we can do is we can make one of the readers be the primary one, and this is the one that will do throttling. This is the one that will control the writer in terms of how much the writer is allowed to write. In the example I gave, it's probably the audio, the speaker. Then the secondary consumers are just trying to keep up with the data as best they can, but it's okay if they're not able to. And so if they overflow, it's fine as long as they know about it. Here's a visual for that. Here's the kind of multi-consumer that Timur talked about, and then here's the other kind, which is the broadcast, where all of the consumers receive the same data, and in this case, this one wasn't able to keep up quickly enough, and so lost the data. For this to work, you have to have multiple read indices. You'll have a common write index, and then each reader maintains their own read index. And the writer will only look at the primary read index for flow control. It just gets too complicated if the writer is throttled based on multiple readers. Let me skip this. Okay, security. So we talked about 2 security areas so far related to the integer arithmetic and then also invalid indices. The final security area, how many more minutes? 3, okay. The final security area is multiple processes. Imagine if your reader and writer are in different processes and they don't trust each other. You know, one is a client, one is a server, but neither one trusts the other side. So, let me skip, okay. So let's suppose we have these multiple processes. The green little fishies represent threads, and the magenta represents processes or address spaces. They share some common resources. In this case, they share the circular buffer or queue, but they don't trust each other. So here's our queue and shared memory. So the way we can handle this is by being really, really careful about where we put the indices and where we put the array, right? So basically, for example, the writer's index is read-only with respect to all of the readers. Right? And if you have secondary readers, the writer doesn't even need to know about their indices. So by doing this and then also combining it with protection for the data buffer, you can have a safe situation where you can have one writer, multiple readers, and the readers will not affect each other even if one of them has a bug or a virus or something like that. Okay. So summary is that circular buffers or lock-free queues can be secure. Rear matters, let's see. Okay, so I was talking about my implementation where I'm trying to merge all these 10 or 15 different copies. This is the layering that I eventually came up with. Basically, I have these are the operating system or platform-specific parts. Then there's the index arithmetic, the obtain release section, and then finally a read-write API, which is a lot more friendly to work with. So that concludes my talk. Thank you for coming.